Hello everyone, hope you all are doing well. Welcome to the video lecture on application of operational amplifier. My name is S. Senthilnath and my registration number is 19E093 from Tyagarajar College of Engineering, Madurai. We are going to see two applications of operational amplifier. The first one is wave shaping and the other is square wave generators. So the question arises in our mind is, what is wave shaping? Let's find out the answer. Wave shaping technique include clipping and clamping. This clipping can be divided into positive clippers and negative clippers. Same way, clamping can be divided into two parts, positive clamping and negative clampers. In operational amplifier, clipper circuits uses a rectifier diode may be used to clip off a certain portion of the input signal to obtain a desired output waveform. The diode works as an ideal diode because when on, the voltage drop across the diode is divided by the open loop gain of the operational amplifier. When off, the diode is an open circuit. In an operational clamper circuit, however, a predetermined DC level is deliberately inserted in the output voltage. For this reason, the clamper is sometimes called a DC inverter. As I previously mentioned, clippers can be classified into positive and negative clippers. First, we can look into positive clippers. A circuit that removes positive parts of the input signal can be formed by using op-amp with a rectifier diode. This is the positive clipper. The clipping level is determined by the reference voltage V reference, which should be less than the input voltage of the operational op-amp. That is, V reference should be less than V input. The output voltage has the portions of the positive half cycles above V reference clipped off. Before looking into the working, first we can see the circuit diagram. This is the positive clipper circuit. It has diode D1 and resistors and an operational amplifier and a V input. The condition should is V input should be less than V reference. Please have a close look at this circuit, which will help you with better understanding of this concept. Okay, now let us see the working. The circuit works as follows. During the positive half cycle of the input, the diode D1 conducts only until V input is equal to V reference. This happens because when V input is less than V reference, the output volts V0 of the operational amp becomes negative to device D1 into conduction. When D1 conducts, it closes feedback loop and the operational amp operates as a voltage follower. That is, output V0 follows input until V in is equal to V ref. That is, V input is equal to V reference. When V input is greater than V reference, the V0 becomes positive to derive D1 into off. It opens the feedback loop and operational amplifier operates open loop. When V input drops below V reference, the output of the operational amplifier V0 again becomes negative to device D1 into conduction. It closes the feedback path. Thus, diode D1 is on for V input is less than V reference and D1 is off for V input is greater than V reference. The operational amplifier alternates between open loop and closed loop operation as the D1 is turned off and on respectively. For this reason, the operational amp used must be high speed and preferably compensated for unity gain. So this is the positive clipper circuit as I shown before. Now let us look at the input and output waveforms. In the left side we have input and output. See, the V reference is equal to 1 voltage and the input is a sine wave shown here. After it passes through the clipper, the portion above the reference voltage is clipped off and the portion below the reference voltage remains same. And again see in the right side we have input and output. Here the only difference is reference voltage is minus 1 volt. So here the major portion that is above is clipped off and the portion below remains same. Next we have look at a negative clipper. The positive clipper is converted into a negative clipper by simply reversing diode D1 and changing the polarity of V reference voltage. The negative clips of the negative parts of the input signal below the reference voltage diode. D1 conducts when V input is greater than V reference, and therefore during this period output volt V0 follows the input volt Vin. The negative portion of the output below negative V reference is clipped off because D1 is off and V input is less than minus V reference. If minus V reference is changed to V reference by connecting the potentiometer RP to the plus VCC, the V0 below plus V reference will be clipped off. The diode D1 must be on for V in is greater than Vref and off for V in. The working is similar to that of the positive clipper, but the polarity and the diode is reversed. Here you can see the circuit diagram for negative clipper. You may see that the diode D1 is reversed and the polarity is changed. Remaining all are remains quite same. And now let's have a look at into input and output waveforms. In the left side, uh, input is a sinusoidal wave and we have the V references minus 1 volt. After passing through negative clipper, the portion below the reference voltage is clipped up and the above portion remains the same. The similar thing is illustrated when V reference is taken as 1 volt in the right side. Okay, now it's time to look into positive and negative clampers. In clamper circuit, a predetermined DC level is added to the output voltage. The output is clamped to a desired DC level. This is what we have seen earlier. If the clamped DC level is positive, the clamper is positive clamper. If the clamped DC level is negative, the clamper is negative clamper. Other equivalent terms used for clamper are DC inserter or restorer, inverting and non-inverting that uses this technique. So now we can have a look at positive and negative clampers and the input and output waveforms. It has a capacitor C1, C2 and resistors and an operational amplifier, and the input is given through Vin. Closely observe the wave circuit for negative and positive clamper so that you can have a better understanding on these subjects. And you may find the input and output waveforms for the clipper and clamper below. Next, another interesting circuit is peak clamper circuit. Have a look at this circuit. It is the peak clamper circuit. Okay, now we can see this working. In this circuit, the input waveform peak is clamped at Vref. For this reason, the circuit is called the peak clamper. First, consider the input voltage V reference at the positive input. Since this voltage is positive, V0 is also positive, which forward biases D1. This closes the feedback loop. Voltage Vin at the negative input. During its negative half cycle, diode D1 conducts charging C to the negative peak value of Vp. During the positive half cycle, diode D1 is reverse biased. Since this voltage Vp is in series with the positive peak voltage Vp, the OP voltage V0 is equal to 2Vp. Thus the net output voltage Vref plus 2Vp. So the negative peak of the 2Vp is at V reference. For precision, clamping Ci Rd is very much lesser than T by 2, where Rd is equal to resistance of the diode D1 when it is forward biased. T is the time period of the input waveform. Resistor R is used to protect the operational amp against excessive discharge currents from the capacitor C, especially when the DC supply voltage are switched off. A positive peak clamping is accomplished by reversing D1 and using negative reference voltage. The main difference between peak clamper and the uh, Positive and negative clamper is that positive and negative clamper have fixed DC level and peak clamper can have variable DC level. Okay, now we can have a look into the another application of operational amplifier, that is square wave generation. So first, what is square wave generator? A square wave generator is an electronic circuit which generates square wave. This section discusses about operational amplifier based square wave generators. Now we can have a look at the simple diagram of a square wave generator. It has a capacitor and 3 resistors and an operational amplifier, and R3 is grounded. Observe that in the circuit diagram shown above, the resistor R1 is connected between the inverting input terminal of the operational amplifier and its output of operational amplifier. So the resistor R1 is used in negative feedback. Similarly, the resistor R2 is connected between the non-inverting input terminal of the operational op-amp and its output. So the resistor R2 is used in positive feedback path. A capacitor C is connected between the inverting input terminal of the operational amplifier and ground. So the voltage across capacitor C will be the input voltage at this inverting terminal of operational amplifier. Similarly, a resistor R3 is connected between the non-inverting input terminal of the operational amplifier and ground. So the voltage across resistor R3 will be the input voltage at this non-inverting terminal of the op-amp. Now let us look into the operation of a square wave generator. Assume there is no charge stored in the capacitor initially. Then the voltage present at the inverting terminal of the operational amplifier is 0 volts. But there is some offset voltage at the non-inverting terminal of the operational amplifier. Due to this, the value present at the output of the above circuit will be plus Vsat. Now the capacitor C starts charging through a resistor R1. The value present at the output of the above circuit will change to minus Vset when the voltage across the capacitor C reaches just greater than the voltage across the resistor R3. The capacitor C starts discharging through a resistor R1 when the output of the circuit is minus Vset. The value present at the output of above circuit will change to plus Vset when the voltage across the capacitor C reaches just less than the voltage across the resistor R3. Thus the circuit in the above diagram will produce a square wave at the output as shown in the following figure. This is a typical square wave whose values can be either plus Vset or minus Vset. From the above figure, we can observe that the output of a square wave generator will have one of the two values, plus Vset and minus Vset. So the output remains at one value for some duration and then transition to another value and remains there for some duration. In this way it continues. Thank you for the opportunity. Thank you.